All right, we're going to continue our journey into the application of derivatives, and this actually in the textbook begins in chapter 4 here with linear approximation. I kind of consider rates of change and related rates type problems that we've been working on as being applications of the derivative, and those in the textbook though are in chapter 3. So chapter 4 really begins applying the derivative, and we're going to look at the idea of linear approximation. So when you say linear approximation, I just want you to think tangent line approximation, because that's really all we're doing. There's going to be a lot of new notation maybe and some new words, but essentially just remember that this is really using the tangent line essentially to approximate the value of the function. And this is actually real important in evaluating values. For instance, we take for granted, I think, very much the fact that I can use a calculator and deduce what sine of, say, sine of 1.7 is equal to. What is sine of 1.72 is equal to? I have no idea. If I use my calculator, right, punch it in, I get a result. But the question is, how does that calculator do that? Okay. Well, it may not be exactly using linear approximation, but a lot of times functions can be approximated, the values of functions, with the tangent line. Also, these linear approximations are useful later on, especially if you're in engineering or physics, areas where you'll deal with somewhat more complicated equations, for instance, and by doing some linear approximation, you can make find an estimate, if you will, to the equations using this method, and basically get a good estimate in an easier way than trying to solve the actual equation, which may be very difficult or impossible to solve. So linear approximation, very important in lots of areas in engineering and elsewhere. So a couple things we're going to denote. We're going to talk about a function f over an interval, and I'm going to go from a to a plus delta x. Okay, this delta x is like the h that we've used before. You remember in the limit definition of the derivative and stuff, but we're going to use delta x here. So that's what I'm saying. There's a little change in notation here. And we're going to denote the change in f. Sometimes this could be considered the change in x. Okay, so the little triangle or Greek letter capital delta denotes change in a quantity. So change in f or change in, sorry, I said x. I meant to say y. Change in y. Okay, change in x, of course, is a horizontal change. Change in y being a vertical change, and we're looking at the graph. And here's the definition for the change in f or change in y. Okay, so let's just take a look at what we're talking about here. Let's suppose that the value of a is somewhere like here. Now you so maybe right here is a 2 point something, whatever it is. And the solid line is the graph of the function f. That's the graph of the function f. The dashed line, this is the tangent line essentially, right? This is the tangent line to f at x equal a. Okay, and so of course this point right here is the point of tangency, right? It's on the tangent line, but it's also on the function. So it's a comma f of a is that point. Okay, and then I'm gonna let delta x be a positive value, and so I'm gonna delta x will be some positive quantity. Let's just say that delta x is the distance from here to here, the change in x, delta x. And so what's this point right here? We can say this is a plus delta x. Right? A plus delta x. And if I come up here, then what's this point right here? That is the point a plus delta x, comma f of a plus delta x. That's that point there. Okay, so far you're getting the feeling this is very similar to that setup we had for the just finding the equation of the tangent line. Okay, now we do know the slope of this line. What's the slope of this line? What's going to be f prime of a, because it's the tangent line at a, so it's the derivative at a. Whatever the derivative at a is, that's going to give us the slope of this line, right? The slope of the tangent line is f prime of a. Okay, so first of all, let's talk about this change in f or change in y value here. That's as I go from this point a comma f of a. So I'm going to draw a horizontal line from here to a plus delta x, f of a plus delta x. All right. This is the vertical change, the change in the value of the function. Okay, or again, it could be change in y, depending on either notation's used. So the function is y as a function of x. Okay, and so that's the actual change in the function. Now, what we're going to do here is a linear approximation. So I can approximate this change in f, the change in the function, as I move from a to a plus delta x, as I go over this interval, right, this of length delta x, this change in f, I can approximate it using the tangent line. Okay, so if I instead travel along the tangent line and look right here at this point here, right, then this going from this point to this point, the change in height, okay, we're going to designate that as dy or df, dy or df, okay, and this is something that we call a differential. So what would the value of dy be? And we'll talk about why we call it dy. It kind of sounds familiar, doesn't it? So we've got dy or df. Okay. So what is that thing equal to? What is that thing equal to? Well, if you think about this here, if I wanted to, I know the slope of this, right, is what? F prime of a. That's the change in y over the change in x, right? Slope is change in y over change in x, right? So this is essentially, we can think of this as being the change in y over the change in x. But in this case, it's going to be really the dy over dx, right? I mean, that's the derivative, dy over dx. So we think about dy and dx being a very small change in x, and dy as being the corresponding small change in y, then we can find the value of dy from this fact. I'm going to let this be equal to this dx. Okay, so my delta x and my dx are going to be the same, but obviously my delta y or delta f and my dy or df are not the same. How do I find this dy? Well, I'm going to simply multiply the slope by the change in x, delta x, or dx, either way. I'm going to multiply it by the change in x, and that will give me dy. Since, right, it's the rise over the run. If I multiply it by the run, I get the rise, I get the change in y. And so here it is, dy is equal to the slope, which is f prime of a, times delta x, or dx. Okay, or dx. Now, what's the difference between the delta x and the dx, the delta y and the dy? Well, the d is again thinking of a very small change, very infinitesimally small change in y, or infinitesimally corresponding change in x. And you can see as delta x gets smaller and smaller and smaller, that's what we're thinking. Notice that the difference between dy, our differential again is what this is called, and the delta f, or delta y, they're going to get closer to one another, right? In fact, real important here, this vertical distance between these two values is what we refer to as our error. That's how much the change in f or change of y differs from this so-called differential. So this thing again is called the differential, or a differential, I guess. And this error, I can compute this error that I had up here. What is this error equal to? It is equal to, and again, when I'm interested in this error, I'm only interested in the actual distance. I don't care if it's negative or positive, so the way I subtract doesn't matter. So I would like to take the absolute value of the actual value of the function, a plus delta x, evaluated, f evaluated at that input, right, minus what the value of dy. Right. So sorry, this should be not f plus delta x. This should be change in f. I'm sorry, my notes all messed up. This should be change in f or change in y. Right, the actual change that we're looking at versus the approximation, the linear approximation. So this linear approximation is good. You can see that error here between these 2 points is pretty small, especially as delta x gets smaller. As we get smaller and smaller value, right? This change is very small. Now the difference gets really bad as we continue to move out. If this function continues to move, then that error gets bigger and bigger. But in an error interval close to a, these two graphs, the function and the tangent line, almost look the same, don't they? So we're real close, right? That's the linear approximation we're talking about. And so, just in summary, the linear approximation to the function y equal f of x at x equal a uses the vertical change in the tangent line, right, dy, that's called the differential, to approximate the change in y. So delta y is equal to, again, this change, right, this is the actual change, and the differential dx is equal to delta x. Okay, but the dy, which approximates the change in y, is going to be f prime of a times dx, and that's what we were doing right here. Okay, so here's our graphical situation that we talked about, and here are the definitions, if you will. But again, all we're talking about is essentially use the tangent line to approximate the function. Now you might say, why do we do that? Right? Why do I need to approximate a function? I just punch it into my calculator. Again, the question is not to be button pushers, right? Or the topic of this course is not to teach you how to push buttons. The question is, how does it actually work, right? What's going on? How did they program the calculator to do that? How do they figure out the sign of a certain value, for instance? Well, linear approximations is one way we can do that, in a sense. So here's some typical types of problems here. Let's estimate this quantity here for the function f of x equals 1 divided by x plus 1. And we're going to just estimate the change in f as x varies from, basically notice we're going from 3 to 3.02. So back into this picture here, this right here, the 3.02 is the a plus my delta x. And the f of 3 is the a. So we're going to backwards piece together. What do I have? Therefore, a must be equal to 3, and my delta x must be equal to what? 3 plus what equals 3.02? Well, I need a change of 0.02, right? If I add that to 3, I get 3.02. Right? This is the same thing as dx here. Remember, it's the same thing as delta x and dx are equal to one another. Okay? And then, of course, here I have f of x, and what am I going to need to find my differential? Notice again, this is an application of the derivative, right? And so we need the derivative. So we need to take the derivative of this function. In order to do that, I'm going to rewrite this. You could use the quotient rule, but I'm just going to rewrite this since it's a constant up top. 1 divided by x plus 1 is just x plus 1 to the negative 1 power. And so I can find my derivative using the chain rule, right? The outer function is u to the negative 1, inner function is x plus 1. So derivative of the outer function is negative u to the negative 2, that's the power rule, times the derivative of what's inside. But if you think about it, that is just equal to 1. Right? The derivative of x plus 1 is just equal to 1. And so my answer is that f prime of x is equal to negative 1 over x plus 1 squared. Okay. And now we're just going to estimate, right, the change in the function here. Again, change in y or change in f are used interchangeably, as I said. So again, this could be the change in f as well. So that's what we're looking for, estimating the change in f. So the change in f is approximately this differential dy, which is equal to f prime of a times dx. Okay, and remember a was 3, right? A was 3, so I'm plugging that into here. So this is equal to what? This is equal to negative 1 over x is 3 plus 1 squared, right, times dx. Well, what was dx? Dx is 0.02. So what's this become? I can simplify this. 3 plus 1 is 4. I get negative 1/16 times 0.02, which I can write as, if I want to get an exact value, I guess negative 1/16 times 0.02 is 2/100ths. 2/100ths. I can do a little simplifying here, right? And I get negative 1 over 800, which is negative 0.00125. So there's my estimate for the change in f using linear approximation. Now that's not the exact change. If you wanted to know what the exact change was, you could use technology, a calculator, to plug in, right, and figure out what is 1 divided by 3.02 plus 1, or 1 divided by 4.02. Get that expression approximated, and then subtract f of 3, which is going to be 1/4, 0.25, and you can get this value then. Okay. But again, this is the approximation from the tangent line. Okay. As long as delta x is relatively small, which, we're pretty small here, then the approximation is fairly good. Okay. In fact, let's just see what that actual value would be in comparison. It doesn't ask to find the error here, but if I wanted to look at the actual f of 3.02, and the function f of x is 1 divided by x plus 1, 1 divided by x is 3.02 plus 1, right, which is that, minus 1 divided by f of 3 would just be 1/4, right, or 0.25. Okay, so there's the actual. This is what I'm approximating with. So is it a pretty good approximation? Yeah, pretty good. It's accurate at least to the 4th decimal place, and almost to into the 5th decimal place. So pretty good approximation. All right, let's do another example. Let's estimate delta y at x equal pi over 4 using differentials if y is tangent x and dx is 0.04. So just looking at different ways that these problems could be worded. So notice this is the point we're taking, if you will, the point of tangency at x equal pi over 4. So that's our value of a. And remember that delta y can be approximated as the differential dy, which is f prime of a times dx. Now I've got dx right there. I need f prime of a. Of course, here our function is y equal tangent x, so we'll say that's our function f of x. So y equals tangent x. What am I going to need? I'm going to need the derivative, right? So what is the derivative of the tangent function? That's secant squared. Right? And so using that information, then this is the derivative evaluated a. What's a? Pi over 4. So this is going to be secant of pi over 4 all squared, right? Because that's what secant squared means, right? Secant of x, and then squared is what secant squared x means. All right, so there's that piece, times delta x, which is 0.04. Okay. So then we can evaluate this. What is secant of pi over 4? Well, secant's the reciprocal of cosine. Cosine of pi over 4 is square root of 2 over 2, or 1 divided by square root of 2. So the reciprocal of 1 divided by square root of 2 is just square root of 2. So that's secant of pi over 4. And if I square the square root of 2, I get 2. This is 2 times 0.04, which is 0.08. And there's my estimate for this change in y for the function tangent x. Right? Starting at a equal what? Pi over 4. And with a change in x of 0.04, then the estimated change in the value of the function is 0.08. Okay, so if I didn't have a calculator at all, and I needed to estimate, the change in the tangent function from pi over 4 to pi over 4 plus 0.04, how would you do it without a calculator? Well, here's one way you would do it. You'd do it this way. You don't really need a calculator to do any of this, right? You might need to, approximate this down here, but since we've got a nice answer, it turned out pretty good. But that's the idea, or at least at any rate, we don't need to deal with the actual tangent function itself. Evaluating at points we don't know the exact value of. So another way, here's the idea: estimate the square root of 17 using linear approximation, and then we're going to find the error using the calculator, of course. But what if I say, find the square root of 17? You just say, I'm just going to punch it in my calculator. Right? I can do that in my calculator. But the question, what if you don't have your calculator? How do you do it? Okay? Or how does that actually work? How does the calculator find the square root of 97, which is not a perfect square? How would you go about doing that? Well, there's algorithms and different methods, and we're going to look at a method later on in the course called Newton's method to help estimate it. But here we're going to do it with linear approximations. And here's the way you're going to think about it. Think about, I don't know what the square root of 17 is. It's not a perfect square. But there is a number close to 17 that I know is a perfect square. And what is that? 16, right? Well, how does that work? Well, 16 plus 1 is 17. So this is the way I'm going to think about the square root of 17 is 16 plus 1. And this is going to be my f of a plus delta x. Okay? Now please note that this is not equal to the square root of 16 plus the square root of 1, which is 4 plus 1, 5. Okay? Square root of 17 is not 5. I hope you know that, right? So I can't do that. I have to leave that like that. Okay? But this tells me then that a is 16, right? The delta x is 1, and the function we're talking about, f, is what? The square root of x, or x to the 1/2 power. Okay? And so again, what are we doing? Let's just draw a little picture of this. If you remember the graph of the square root function looks something like this. Okay, and out here somewhere is 17. I'm trying to estimate that value. What is that value here is the question, right? Well, 16 I know is nearby, and I come up here. 16 I know what that value is. Square root of 16 is what? 4. I know that's 4. If I zoom in on this little area here, let me just sort of zoom in, blow up that area, sort of exaggerate the graph too. What we're doing graphically is, all right, at 16 versus at 17. Okay, so I know this output, this height is 4. The question is, what's that height? Well, I don't know if I don't have a calculator to do it. But what I'm going to do is use the tangent line to approximate this. And so, if I can find what I do with my ruler, my ruler has magically disappeared on me. It's the invisible, the vanishing ruler. Wow. Quite amazing. Okay, improvise, I guess. No idea where it went. what I'm going to do is I'm going to print line to this function. So right here at 16, right, where I know the value of the function, right, 16, square root of 16 is 4, so I know that point is 16 comma 4. I'm going to approximate, right? So what I'm going to end up with is, actually this height as an approximation. Okay, that's going to be, and so there is going to be an error here, right? The difference here to here, right? That distance right there will be my error, but that's going to be my estimate. Okay, so that's what I'm going to do. So we've got our change, in f. As I move from this point to this point, this right here is the change in the function f. And the change in f is, remember, f of a plus delta x minus f of a. And in this, in terms of our language here, using these values, right, this is f of 16 plus 1 minus f of 16. Okay, I know what this is, right? F of 16, since f of x is the square root of x, as we said, this is the square root of 16, which is 4. Okay, this 16 plus 1 is 17. This is the square root of 17. This is what I'm trying to find. Right, this is what I'm trying to find. So keep in mind, this is the equation we have here that basically is going to say that the change in f is the square root of 17 minus 4. And what I'm going to do now is estimate this with the differential. So the change in f is approximately df, or dy, which is f prime of a times dx. Remember, dx is the same as delta x. By the way, we need f prime of x, right? So what do we have for f prime of x? Just power rule, right? This we've done a million times. Bring the 1/2 down, subtract 1. And so it's 1 over 2 square root of x, right? X to the negative 1/2 is 1 over x to the positive 1/2. Okay. And so in this case, what do we get? F prime of a, what's a? 16. This is 1 divided by 2 times the square root of 16, that's that piece, times dx, which is what? Just 1. Square root of 16 is 4, 2 times 4 is 8. This becomes 1/8, which is 0.125. Okay? And so that is what I'm going to go plug in that over there. And so 0.125 equals the square root of 17 minus 4. So what is the square root of 17? Add 4 to both sides. Square root of 17 is 4.125. Well, again, approximately, right? We're approximating that. There's our approximation. Okay. There's the estimate using linear approximation. And it's not the same thing, right? So it's going to be actually, if you look at this graph, right, a little bit higher. Our estimate is up here on the tangent line. It's not on the actual curve of the square root function. Okay. Now, what is our error? What is our error? Well, it's the absolute value of the square root of 17 and our estimate, right? Okay, so now I am going to use the calculator. Let's see what the square root of 17 is, right? So you've probably already done that. Just saying, what in the world is he doing? Oh, just do this, right? There's our answer. But again, the question is, how does the calculator give you this value? That's another question, right? But you can see then, all right, so I can do this with calculator. And we get 4.123105626, blah, 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 right? But there it is. And you can see the estimate that we have is a little bit bigger than the actual value, and you can see why graphically in this case. So sometimes, depending on the tangent line, we might be, a little bit above the actual value, You know, if the tangent line comes below, we might be a little bit below. Okay, but there is always going to be that error. We only want the absolute value, so it doesn't matter how we subtract this. But if I subtract 4.125 from this, of course I do get a negative value, but I take the absolute value, and so this is about 0.00189. So that's how much we're off by. That's the error. Okay. And so it's important to keep track of your errors. You do these linear approximations if you're solving problems. How, you know, is it okay? I mean, some problems it's okay to be off by a little bit. Others you need a little bit higher tolerance, and so you have to be careful about that. Okay, I'm going to go through and just finish this off with this last problem. I was going to do 2 videos, but I'm just going to do one. It'll be a little bit longer than typical, but the last thing I just talked about is this so-called linearization of a function at x equal a. What's the linearization? I can't even say it. Here's what the book will show you, or you'll look up, or you might find this. L of x is f of a plus f prime of a times x minus a. Okay, what is all this stuff? All right, and this is for x close to a. Then the linearization is about equal to the actual function. So what is this linearization? So here it is. This is just the tangent line. Of course, at x equal a. This is just the tangent line at x equal a. That's what this thing is. Okay, and in fact, you know, the tangent line, the slope is what? F prime of a. All right, and what's your point of tangency? Where are you tangent to the function? At a comma f of a. All right, remember this would be the x value, this would be your y value. And what would it look like if you find the equation of the tangent line? What would it look like? Well, you would have y here. This is the let's do the x1 and y1, right? This will be your y1, and this will be your m x minus what? x1. Right, it's kind of solved for y, right? You'd actually have y minus y1 equals m times x minus x1, but I've brought the y1 over here. So the y1 is what? The same as f of a. The x1 is the same as a, and m is f prime of a. So you see, this is nothing more than exactly the tangent line. Okay, so when we say find the linearization, you just find the equation of the tangent line. So find the linearization of f of theta equals sine squared theta at theta equal pi over 4. Okay, so at theta equal pi over 4, notice a, the value of a we're talking about here is pi over 4. We're doing it at that value of the independent variable. I also need to find the derivative, right? What is f prime of theta? Well, be real careful, right? Sine squared theta, I can think of as sine of theta squared, or sine theta times sine theta. I can use the product rule, but I'm just going to use the chain rule. I've got outer function u squared, inner function sine theta. So what's the derivative of u squared? That's 2 u to the first power times the derivative of what's inside. What's the derivative of sine of theta? Cosine theta. Right? So this is by the chain rule. Okay, and so our slope, right, our f prime of a, right, the slope of our tangent line is that, and I just plug in now the sine of pi over 4 is the square root of 2 over 2, or 1 divided by square root of 2. If you rationalize it, it's square root of 2 over 2, same thing. Cosine is the same thing of pi over 4. Remember, sine and cosine of pi over 4, they are equal to one another. You again, refer to the unit circle or draw your corresponding right triangle. So if I multiply these two, what is 1 over the square root of 2 times 1 over the square root of 2? That's just a half. And what's a half times 2? That's just equal to 1. So our slope is 1. Right? What's our point of tangency? Well, f of a in this case is f of pi over 4. So now I go into the original function here. What is sine of pi over 4 all squared, right? Sine squared. So the actual point on the graph, sine of pi over 4 again is 1 over the square root of 2. If I square that, I get 1/2. And so what's our equation? The point of tangency is a, which is pi over 4, comma y, which is 1/2. So here's the point of tangency. And so we have our slope and our point. So it's y minus y1, which is 1/2, equals slope 1, right, there's our m, times x minus x1, which is pi over 4. So if I add 1/2 to both sides, I get y is equal to 1/2 plus 1 times x minus pi over 4. Okay. Now this is in the form that we have up here. So f of a is 1/2. F prime of a is 1. X minus a is x minus pi over 4. But this, this is basically just the tangent line. That's a linearization. So in other words, when I see this function, right? Oh, I'm using the wrong variable, and I've got theta here. This should technically be a theta. Sorry about that. Should be a theta. Okay, but because the independent variable is theta. If this was x, we would have x. Same thing. But here's the thing: this function here and this line, if I graph them for values close to pi over 4, they are essentially very similar. And so I can, instead of using sine squared theta in an equation, trying to deal with that, I can replace it with this expression. Again, as long as theta is close to pi over 4. If I move away from pi over 4, then my linear approximation is not so good. Let's do one more just for practice. We'll close with this. Let's find the linearization for the inverse tangent function at x equal 1. All right? So dealing with the inverse tangent function, hard to do just using the function. But here we can find the linearization, which is just the equation of the tangent line at x equal 1, right? So again, x equal 1 implies that a is the point, right? We're taking it at a is 1. What's the derivative of the inverse tangent function? Should know that. We talked about that. There it is. So what's our slope? It's equal to f prime of a. So a is 1. I plug into the derivative at 1, and I get a slope of 1/2. What is the point of tangency? What is f of a? What is f of 1? Well, it's tangent inverse of 1. Now, I do need to evaluate tangent inverse of 1, but that's easy. Tangent inverse of 1 is what? Pi over 4. That's because tangent of pi over 4 is 1. So you do have to be able to evaluate inverse trig functions and get the exact value, not just approximations. Okay? And we can do that for specific values only, right? So I would only expect you to do this if it was tangent inverse of 1, tangent inverse of square root of 3, tangent inverse of square root of 3 over 3, etc. Those types of values. Okay, so our point of tangency is a comma f of a. A is 1 comma f of a pi over 4. So the tangent line is y minus y1 equals m, which is 1/2 x minus 1. Add the pi over 4. And you can distribute the 1/2 if you want. But I'm just going to leave it in this form. Typically, again, I didn't use it above, but the y is the linear approximation. Sometimes L is a function of, in this case, it is x, not like theta, like it was above. And here's my tangent line approximation. So again, here's the importance of this. This function here, you can use this function to evaluate the inverse tangent function, to evaluate this function. As long as you're close to x equal 1 for like 1.002 or or 0.998 or something like that, some value that's close to 1. If you plug it into here, you're going to get a very good approximation. And you think about it, here, if you didn't have a calculator, a lot of you wouldn't know what to do. What is tangent inverse of 1.02? Well, I have no idea. All right, I need a calculator to approximate. What is this, 1.02? Now, you might have to approximate pi is about 3.14, and do that approximation. But you can get that value pretty easily here. So linear approximation, again, very helpful for some of you later on in your careers for sure. But when we talk about linearization again, just remember linearization is nothing more than finding the tangent line. It's something we've already been doing. Okay, so that's linear approximations, and that's it for this lecture.